The James Webb Space Telescope has just captured a phenomenon that defies our standard timeline of cosmic history. Deep in the ancient universe, just 570 million years after the Big Bang, lies a tiny, compact galaxy harboring a supermassive black hole that is growing at an alarming rate. Designated as CANUCSLRD-Z 8.6, this galaxy is essentially an infant, chemically primitive and unformed, yet it contains a monster. The black hole at its core is far heavier than our current theoretical models say it should be for such an early epoch. To understand why this is so shocking, consider that the universe is 13.8 billion years old. Finding a fully formed giant this early is like walking into a nursery and finding a toddler capable of lifting a car. It defies our understanding of biological, or in this case, cosmological, growth limits. This anomaly forces us to ask difficult questions. How did the first black holes come into existence? How did they get so big so fast? And how did they shape the primitive galaxies they lived in? In this video, we're going to break down this groundbreaking discovery, the science behind it, and how it changes the story of our universe's origin. Let's dive in. The object in question, CANUCS LRD-Z 8.6, is part of a mysterious class of celestial bodies that astronomers have dubbed little red dots. To the eye, they look like faint crimson specks. This color is due to the expansion of the universe, which stretches their ultraviolet and visible light all the way into the infrared spectrum. Because the James Webb Space Telescope was built specifically to detect these infrared wavelengths, it is the only tool we have capable of analyzing these ancient systems. For decades, the Hubble Space Telescope scanned similar deep fields, but missed objects like this entirely. They were effectively ghosts in the machine, invisible until Webb's infrared eyes pierced the cosmic dust. This proves that our census of the early universe has been incomplete until now. Interestingly, we can only see this specific galaxy because it sits behind a massive cluster known as MAX J1149. The cluster acts as a gravitational lens, magnifying the faint light from the background galaxy just enough for us to catch it. Without this natural cosmic magnifying glass, CANUCS LRD-Z 8.6 would have likely remained invisible to us forever, hidden in the sheer darkness of deep space. It is a stroke of luck that allows us to peer back over 13 billion years. When researchers pointed Webb's near-spec instrument at this target, the data returned something far more complex than a simple nursery of new stars. The spectral reading showed gas that was highly ionized, along with broad emission lines. In astrophysics, this is the smoking gun for an active galactic nucleus, a region being churned up by a hungry black hole. The gas in the galaxy's center is moving at incredible speeds, driven by the immense energy of a black hole that is actively feeding. By analyzing the light, the team calculated the black hole's mass. Even accounting for the margin of error at such extreme distances, the conclusion is inescapable. This black hole is a giant compared to its host. It is vastly more massive than it should be relative to the small amount of stars in the galaxy. Furthermore, the galaxy is chemically pristine. It lacks the heavy elements that are usually forged over eons by dying stars, proving it is still in the earliest stages of development. And yet, despite the galaxy being in its infancy, the black hole inside is already mature and consuming matter aggressively. Crucially, this object is not a quasar. Quasars are blindingly bright beacons that appear later in cosmic history. This is something different. It is a dim, compact object, giving us a rare glimpse into the teenage years of a black hole before it ignites into a full-blown quasar. By catching it in this specific phase, compact, dim, and chemically pure, astronomers are finally seeing the missing link in how supermassive black holes begin. This finding also solves a mystery regarding the little red dots. Scientists weren't sure if they were powered by starbursts or black holes. Now we know. At least some of these red specks are hiding ravenous black holes. This suggests the early universe was teeming with these hidden giants, far more than we previously imagined. The true disruption here lies in the math. This discovery breaks the golden rule of galactic evolution, the correlation between the mass of a galaxy and the mass of its black hole. In our modern universe, these two distinct objects grow in lockstep. A bigger galaxy typically means a bigger black hole. It implies they evolve together, influencing one another. But Canucks LRDZ 8.6 destroys that ratio. It is a heavyweight black hole sitting inside a featherweight galaxy. To put this in perspective, imagine seeing a massive skyscraper standing alone in a small village of huts. It simply doesn't fit the landscape. This suggests that in the dawn of time, black holes didn't wait for their galaxies to mature. It resolves a long-standing chicken and egg debate in astrophysics. Which came first, the galaxy or the black hole? In this case, the black hole seems to have taken the lead, gorging on gas in chaotic environments that lacked the feedback loops that regulate growth in modern galaxies. This creates a timing problem. For a black hole to get this heavy, this quickly, it couldn't have started small. It must have originated from a massive seed. In standard models, black holes start as the remnants of exploding stars, perhaps 10 to 100 times the mass of the sun. But growing from that small size to millions of solar masses takes time that this galaxy simply didn't have. This implies a shortcut in the laws of physics was taken. Scientists are looking at three main theories. First is direct collapse. Imagine a colossal cloud of pristine gas that doesn't fragment into stars, but instead collapses under its own weight, instantly creating a black hole thousands of times the mass of our sun. This bypasses the stellar life cycle entirely, jumping straight from gas to gravity well. Second is the stellar cluster theory. In extremely dense regions, stars might crash into each other repeatedly, merging into a single intermediate mass black hole very early in the game. The third option is super Eddington accretion. This describes a feeding frenzy where a black hole consumes matter faster than the laws of physics usually allow. The chemical purity of this new galaxy supports this third idea. Gas that lacks heavy metals behaves differently. It's easier to crush down, potentially allowing for this kind of hyperspeed growth. Heavier elements usually cool gas down and cause it to fragment, but without them, the gas stays hot and cohesive, potentially dumping directly into the black hole's maw in a continuous stream. This fits a pattern we're seeing with Webb. Again and again, we are finding things in the early universe that are too bright, too heavy, or too organized. We don't have to throw out the Big Bang theory, but we definitely need to rewrite the chapters on how stars and galaxies are born. We have to move from computer simulations to real-world data. Ultimately, finding an active engine in such a tiny system bridges the gap. It explains how we get from the darkness of the early cosmos to the brilliant era of quasars. Canucks LRDZ 8.6 is likely the missing evolutionary step we've been looking for. So, what does this actually mean for the history of our universe? The implications are massive. Primarily, it confirms that the monster wakes up before the house is built. Black holes appear to gain mass rapidly before the galaxy around them can catch up. Secondly, it changes our view of the era of reionization. This was the time when the universe became transparent. If these hidden black holes were common, their intense radiation might have been the key force that burned away the cosmic fog, shaping the intergalactic medium we see today. Thirdly, it shows us the power of feedback. Even in a tiny galaxy, a black hole can heat up gas or blow it away, fundamentally changing how and if future stars can form. This early aggression comes at a cost. By heating the gas so violently, the black hole might actually starve its host galaxy, preventing new stars from forming. It's a cosmic form of self-sabotage that could leave the galaxy dead before it ever truly lived. To confirm these theories, researchers are going back in. They will use Webb for deeper looks and pair it with the ALMA radio telescope to map the cold dust and fuel supply of the galaxy. We are also just scratching the surface of the little red dots. Webb is conducting surveys to find more of them, to see if this overweight black hole is a freak occurrence or the standard for the early universe. And looking further ahead, the next generation of ground-based observatories, like the extremely large telescope, will give us the resolution to see these systems in even finer detail. This single red dot has revealed a chaotic, fast-paced early universe. It suggests that the relationship between galaxies and their dark hearts is far more complex than we ever knew. The universe is not just older than we thought, it grew up faster than we believed possible. As Webb continues its watch, we should expect to find many more impossibilities that will force us to rewrite cosmic history.